Yeah, well,
Yeah,
let's go to I guess let's go to open discussion. I'm not seeing any hands raised or anything.
Anyone is left that knows about moving electric fields and wants to talk about that topic regarding propulsion, I would love to get across E cross B fields and talk about a device that I'm working on that may help in that research.
Yeah, well, go for it. Go for it.
What do we have left? All right, so what we have here, I know the lighting is terrible in this room, so let's see if I can get my cam to adjust. Probably not.
there you go.
Yeah, good enough. So this disc has, you can see 6 segments. 3 of them go to the center hub and go underneath it. 3 of them go to leads that you can see on the top of that center hub. Those are 3 copper conductors that go to the top, and they actually run up through the frame. I can kind of show that. So anyway, on the top side, if I put in charge, I get 1, 2, 3. I get those plates polarized in one direction, and on the bottom side, if I put in charge, I get plates polarized in the other direction. So on the bottom side, this is an insulating disc. These are partially conductive, painted on carbon or graphene containing lacquer pads to counterbalance out a neutralization plate, so that these capacitor plates can effectively have their fields closed, sort of like, a Hall effect array, where the fields close on the bottom side with a material that doesn't allow charge to circulate very well, so it doesn't produce a countermagnetic field. And on the top side, the connecting flux lines would have to radiate outwards into space, and they should stretch at least, I would say the distance between them, which is at the minimum a 1/4 inch at the pitch point, and at the most probably about 1 1/4 inch average between the plate centers. So this will be charged to over 100,000 volts. It's a sanded off CD-ROM, and these are great disc materials to make stuff like this. So what needs to happen is this has got to go in a vacuum bag and be squeezed. It's already got surface dielectrics, and on the back side to cover this up, this other plastic plate, which is good for 50 kV, just simply covers that. And then this whole thing gets sandwiched down, epoxied together. And then there will be 1 small charge contact that comes in through the motor shaft, and 1 small charge contact that comes in through a sphere that's on the top that will have a ion beam pointed towards it to deliver the top plate neutralization charge.
So where's the high voltage going to be applied to?
The high voltage is applied between this side of the disc at the center hub, which is fully isolated up to 160 kV, and the shaft, which is the other side of the disc. That's so those 2 points, the shaft and these 3 wires, which will attach to an electrode, are isolated from each other to 160 kV DC.
Okay, and the charge is going to be in the dielectric?
Yeah, the charge will actually be both in the dielectric material itself and on the surface of the plates.
Gotcha.
Or at least the displacement charge will be on the surface of the plates, because if all the electrons are pulled to one side of the copper pads, then it's going to leave a whole bunch of protons on the other side, so that electric field can still be emitted out. But in either case, the goal of this device is to basically rotate it at a high RPM, at least 5,000 RPMs, maybe upwards of 9,000 RPMs if I can get it balanced early enough, and to have an electric field in upwards of 100 kilovolts, so that I can see what the effects of that electric field are on surrounding objects, space itself, and maybe even test the device in a vacuum, ideally.
So the metallization that you show on the other side, it's a film on the top of the dielectric, or is it?
Yeah, it's a film made of basically nail polish and graphene. And it's semi-conductive, meaning that the charges that get deposited on it or displaced into it from the dielectric will effectively be trapped by it. They won't be able to circulate very well, so there won't be a conduction current that would normally produce an eddy current and a consequent magnetic B flux that might counteract any emitted fields that we get out the front side.
So the electricity that goes into that, the electricity that you're going to put into it, how does that, is it contacts? How does that work?
Yeah, it's physical contact, directly input from a high voltage power supply.
Mm-hmm.
And you measured the dielectric strength of the insulator, so you know that it's going to be able to take 5K. How many kilovolts did you say?
100,000 volts.
100,000. Okay.
So you basically need about 1/4 of a millimeter thickness layering of like Mylar to fully block that, since
Yep.
a full
Well,
millimeter will
you-
block 400,000.
Yeah, in this case, I'm using polypropylene and polycarbonate.
So how are you going to measure the signal that comes? Are you going to use?
Well, I tried a crude experiment with a very large machine that I showed, I believe, before. But this is the floppy disk motor machine. So this can rotate, and I can deposit charges on the surface of either side of this very thin polypropylene disc. Now, this is an interesting material because one side is very smooth and the other side is quite rough. And the reason for that is this is a diffraction lens from the inside of an LED TV in order to spread the light out more evenly for the LCD panel. So the interesting thing is ions like to stick into the pores on the rough side, but they'll blow right off the smooth side. So if I want to end up leaving a negatively charged disk negatively charged, I can put a bunch of electrons in the rough side. I can put a bunch of positive ions on the smooth side, and I can spin the disk. And all the positive ions will fly off, and the disk will suddenly develop a negative potential. And if I then continue to rotate this disk left with the negative potential, it'll develop a scalar field because now it has an unbalanced negative charge that's in motion. And that motion has angular velocity, and I can apply changes in RPMs to the motor to get the acceleration deceleration field plus the angular momentum, which allows me to detect and actually change the vanes on an electroscope that's hanging there and make them, move or bend based on the RPMs, showing me that I actually have a scalar field that changes.
Gotcha.
So this is an optimized version of that designed to enhance the effect in a more controlled way. There we go.
Interesting. Very cool, Jeremy.
So yeah, something curious, but no one, I don't know of anybody that's working on experiments quite like this. Theoretically, if you get enough, okay, space has a variable refractive index. We know that. If we move a large electric field, it's going to produce a longitudinal displacement of charge. It's basically the same thing as an electron experiencing acceleration or moving around a B flux because we're rotating charges around a circular path. So might as well be the same thing as moving charges through a wire, except for not quite, because there's no balanced charge on which to reflect against those charges. So instead, only the electric potential part of the field ends up showing up. We don't actually get a magnetic field. Contrary to Maxwell's equations, there is no magnetic field for the moving charges. They don't produce one because there is nothing to, I guess, create a frame of reference, a stationary frame of reference by which there becomes a field interaction to collapse the wave function. So it just becomes a scalar potential that's only the dot product of each individual charge. And it never neutralizes out. It's an unbalanced or radiated force that you only lose. Sort of like a radio antenna only emits the radio waves. You never get them back.
But the charge that you're moving is the charge that's trapped in the dielectric.
Right. You never lose the charge, but you produce a field that acts as if you've added more charge. So as long as you don't let ions come in and neutralize that charge, you can effectively continuously rotate that thing and continuously produce a scalar field which should be unbalanced and build up over time. Eventually, you should have a whole bunch of charges that want to rush in from all around you and try to neutralize it out. And as long as you don't let them get to you, well, you can develop quite a potential, theoretically. That's what I'm looking for now, is to fundamentally prove that this potential can charge a capacitor. And that will be absolutely proof that there is not only a virtual charge, but that there's power in that field. And that virtual field contains energy that can be reacted against. If there's power, then you can make a force against it. We know that. So the fundamental experiment should prove that. I wish I could get somebody to work with me on it, but no one wants to seem to engage on it.
Hey, what do you expect to see with your experiment? Are you going to test it with the laser interferometer? Is that
absolutely? But I do expect to see something else. What I'm actually looking for is to see a counter torque against space itself. So this device, here's the plan. It spins up to X RPM, and I have some kind of encoder on there that keeps it at exactly that RPM. There's a motor that spins it up, its internal battery pack and internal power supply are all contained within a box that's isolated from the environment and closed. It doesn't matter if there's air in the box or not. Regardless, it's electrically and air circulation wise isolated from the environment. So I spin this thing up. I hang it from a thread so that it's facing basically downwards like this, and hang it from a thread at its center point to balance. And once everything is at a fixed RPM, I then at that point add the charge to the electrodes. And what I expect to see, if the theory is correct that I'm working off of, which is that it should produce a Lorentz force against itself because of the radiated fields not being in the correct position and the plates now reacting against each other at a slight, tiny angle. You know, that's all that it takes for electrons going through a copper wire is a slow velocity. So we only need a slight angle to cause this thing to drag. And what should happen is the whole box hanging from the thread should start to rotate against itself, against the direction of rotation from this device once the electric charge is added.
So do you have a flux meter? A magnetic flux meter?
I do have ways to measure a flux meter, but the problem is that if the impedance isn't infinite, they'll simply discharge the field. And the charge, you know, sort of bend around them. Just like, you know, if you go up every couple hundred feet, or you know, so if you go up every 300 feet, you get like 100 volts, or I forget what the number is. It doesn't really matter in this case. The point is, if you stick an antenna out of the ground that's conductive, or a rod or a flagpole or something, and it just sits there and it's constantly there, the charge field will bend around it and ignore it, and it'll be compressed. So
well, I'm more wondering if you measure, you know, you have your disc spinning, you've created your different segments where you have your metallization, and then you have a little gap in there, right? And then if you could measure with your flux meter, the flux signal, get it close up to the surface of the disc.
Well, I can measure the potential. I can measure, like if I stick my scope probe, even with no, you know, nothing attached to it, just stick the scope probe close to this plate at low RPM with low voltage, you can see the voltage signal swinging up and down.
Okay, and then when you see it, does it have edges, you know, edge effects, kind of like sharp pulses where the edge of the metallization is, and then it stays up and then goes down? You follow what I'm saying? Is it
only if I bring it really close to the surface of the plate? Yeah, I mean, the farther you bring it away, the more sinusoidal it becomes. The closer you bring it, the more square it becomes.
right? So when you do that, can you see? You can see in the signal, you can see the voltage potential will go. It'll have a ringing basically in front of it when it starts over the metallized place part.
Well, you know, there's really no ringing. It's a very direct waveform. You don't really have any inductance in this place because there's no charge moving. The charges themselves are staying fixed in location on the disc. They're not moving around.
Disc. You're just measuring the voltage difference
right.
in the charge in the probe potentially.
The only thing that's really changing is the gradient divergence at the edge of the other capacitor plate, which in this case is your scope probe. So the closer that you get to the plate, the less edge divergence that you get, and the more it acts like a perfect parallel plate capacitor, and the more square wave that cutoff point is when you change your invert polarity. So it just makes sense based on the conventional parallel plate capacitor dynamics.
Well, my point is, you can see that time delay between it when it goes, because you have that space in between, or a little gap where.
Yeah. If I take one scope probe and I place it really close to the wheel, and I take another scope probe and I place it like 2 feet from the wheel, there's definitely a phase difference between those two.
Right.
And that phase difference is the reason why I'm expecting a counter torque against the device itself against space.
Oh, I see. Okay, thank you, Jeremy.
Yeah, no problem. Anyone else? That's what I wanted to talk about.
Yeah, well, I'm a little bit confused on capacitors. Like I said, I'm not a scientist, but the capacitors store the charge on their plates, on the plus and minus. If they're if they're a capacitor that has a polarized capacitor.
This is a big misunderstanding on capacitors, and if you'd like, I can clarify real quick. I've done a huge amount of preliminary capacitor experiments, and and demonstrated those on video and to a number of people to show where capacitors store their charge, how they store their charge, and the variations in the way capacitor materials will respond to external inputs based on the type of materials used. Okay, so there are different types of dielectrics, and they do very different things in terms of how the capacitor stores charge. Example one, I have this stuff. Now this is the same exact stuff we've seen that big disc made out of. Rough side one, smooth side other. In this case, it's not spinning. This is, again, a polypropylene plastic. So what happens is I will take a metal disc like this. I'll place it on one side and ground it. I will take another metal disc, place it on the other side. Between those two discs, I will apply about 50,000 volts, and I will then remove the discs, and this material I then set on top of a plastic cup and set to the side, and proceed to explain how when charges enter the plates, they don't simply displace or polarize the dielectric. Electrons actually leap off one of the plates and they enter the surface of the dielectric, and that pushes the electrons out of the other side, leaving the charges trapped in the dielectric, which is why, even though technically when this plate is here, the charges migrate from the dielectric back into the plate, the fact that if I only remove one plate, the other plate's still there, those charges want to stay attracted to where their counterbalance charges are. So they actually leap back off the plate by the mechanical motion that I add of removing the plate. That's what gives them the energy to leap off the plate and to stick and burrow into the dielectric, which is why they stay there. Now, you can also use ions to deposit them into the dielectric. However, if I were to have these plates positioned some distance away from this same exact material and they never made physical contact, even in the air, as long as I never reached ionization potential and these were smooth surfaces with round edges, no charges would ever actually enter this dielectric. And if I remove the dielectric, the capacitance would change, but the charge wouldn't stay on the dielectric itself. It would actually re-enter the circuit and cause a current to flow back out of the capacitor by removing the dielectric, because there was no physical contact and no ions were ever able to exchange charges. So if that helps clarify where the charge is stored in the high voltage capacitor, I hope it helps.
So in one case you have free electrons, in the other case you don't, what'd you say?
Right. In one case, you actually have charges enter your dielectric physically, and the dielectric thus becomes the storing medium of the charge. In the other case, you have the dielectric that fills the space and changes the refractive index of the physical volume between the two plates, but no charges actually leave the plates and enter the dielectric. The dielectric simply polarizes that space and acts as a much intense refractive index material, just like a lens would for light. And it effectively makes the two plates act as if they were close to each other while still dielectrically insulating them, keeping charges from flowing from between them.
So in
Okay,
the case
well-
where it's in contact, that's where the electrons are free to flow.
Right. So in the case of ceramic capacitors, for example, the charges actually enter the ceramic material. If you were to, rub the plates off after you charge them, the charge would still be in that capacitor. And I did that experiment. I took a regular ceramic radio capacitor, high voltage, and 18 kV cap, and I removed the plates by just using some acid to rub them off. And then I just simply used a tiny little piece of wire to sort of move around and, charge the plates up. And then I took a piece of wire and brought it around the two sides, and arcs formed across the surface, zapped in sort of like the, like that, what do they call that? That zero pinch machine that, you see lightning discharges across the surface, the Z pinch
Jacob's
machine.
ladder.
Yeah, the Z pinch machine. It looked like that, basically. Sparks just ran from the entire surface over to the discharge point to get out of the dielectric, because they were actually being stored in the ceramic itself. So that just proved where they were being kept.
So now in the case where you have the dielectric and there's a gap, and they say an air gap between the two plates, okay?
Yeah.
If you remove the dielectric, there's still a dielectric. It's just that you've changed the dielectric.
Right.
So aren't you still putting because there's no charge that's going to build up on the metal in either case. It's It's
Well, in
not
what
free electrons on the metal that are causing the charge to build up. That's my point. It's in the space between, you're charging up the air gap essentially, too.
Well,
aren't you?
no, it's not quite like that. You have a physical quantitative migration of electrons that move from one plate to the other. You could actually, if you could microscopically zoom in and force them all through the exact same single path, you could count how many actually flow from one plate to the other. There's a quantity of electrons that actually move in that circuit and are displaced. Now, they don't necessarily need to, the electrons from one plate don't actually make it all the way down the wire and all the way over to the other plate. They just simply move out of one plate and they push on all the electrons in the wire, and then some electrons at the very end of that wire then exit that point and they move into the other plate. So they call it a displacement current instead of, saying that the charges physically move, unlike where when you have a Wimshurst machine, the charges are physically separated because they are the same charges. There's no conductive circuit between the individual pads. So when you mechanically move them, that's the second type of capacitor where there is no physical contact and the charges are trapped on the actual metallic conductors themselves, if that gives you an idea.
Okay, thanks. That's cool.
Sorry. Hope it wasn't too complicated. I'm gonna grab something to drink. Y'all take a discuss whatever you want.
What's that?
I said I'm gonna go grab something to drink. I'll be right back.
So let's see. Anyone else got something to talk about?
Well, I think I could come up with something here. When I was younger, we talked about capacitors. I talked about some capacitors to these electronics dudes, and they said that they don't know where the charge is inside the capacitors, or it's like when you generate electricity with a generator, where are all those electrons coming from? Are they generated from the ether? Are the ether generators? I'm confused about that. But I just need to read up on it and study it more. But I've seen it's hard to get the real science when you go through the internet and search this stuff. Like some of these guys are saying one thing, and then you can get the exact opposite of what they're saying from some other expert.
Where the electrical energy was stored in a capacitor. His conclusion conflicts with how physics describes capacitors today. This video will describe that conflict and show you how to prove that Benjamin Franklin was right. This is the basic outline that we are going to follow. Now, why does it matter that we understand how a capacitor works? First,
doesn't apply to vacuum capacitors, just to mention that.
First of all, a capacitor is a very fundamental component in our electronics today. If we were to
Might be useful to look at how they use electrical charges to basically force water flows so that you can do reverse osmosis while repelling other materials that don't go through the charge. Kind of like if you have an empty hose and you turn it on, it takes quite a while before you have any flow of water at the other end. But if you have a full hose, the second you turn it on, that water pressure immediately shows up on the other end because it's pushing that water that's already in the hose out. So.
I do remember some basic videos on the Leyden jar and how they were able to store a charge inside this glass jar or capture electricity in it. Uh, you've heard about the Leyden jar?
Me?
Anyone? I guess
Yeah,
Benjamin
that's
Franklin.
that's actually what Franklin used in his experiments. It was a Leyden jar, and that's why I was asking Remi about where is the charge stored, because because a lot of people think it's in the metal plates, because that's what the free electron theory is, but actually you can take, like Jeremiah has described, you can take that piece of dielectric and set it over here and do a bunch of stuff and then plug it all back in, and it's like a battery. It just stores the charge. So and I feel that's how the so-called vacuum energy works too, is it's a type of dielectric. It has a real high dielectric constant, so you can't, and in some cases it's negative, and that affects the properties that we observe. So, you know, if it's negative, then that's kind of like imaginary mathematically.
You might look into Celeron's backing and research from the Princeton University research they did on the PAIR project, where they were basically using the concept of basically the mind affecting the virtual particles that normally wink back out of existence all around us. But if you were to concentrate on a specific given area, you could create more potential for them to remain and then become a part of the matter and energy that's in the surrounding environment to tip a scale, which is what their think on, think off light is based off of, where they use REGs, random event generators, where basically your mind is attempting to concentrate on that random stream of events to tip them one way or the other. So Celeron.com, people that worked on the original PAIR research project are still basically over there. I don't know if all of them are there. I know some took their research from the Princeton Engineering and Anomaly Research Group and started applying it to epileptic seizures. And they had a lot of success at basically building devices that could detect a seizure from someone using, it hooked up to a computer to gather that data and sift through it. It was able to let someone know after it had tuned up to that person up to 8 hours ahead of time exactly when they were going to have a seizure within 5 minutes, which is much more accurate than a dog can do with whatever they're doing with their ability to sense and recognize an oncoming seizure for someone.
Wow. Wow. Quantum biology.
Right.
So that on that subject of the capacitors and the Leyden jars, I put a link to a YouTube video in the chat, and I just wanted to mention it. It's about 21 minutes, and it talks all about how basically why Ben Franklin's model is better than Maxwell's.
I have a copy of that program. It's kind of abandoned too, where you're basically, their software basically enables you to use your CPU as that random event generator device to switch it on and off. And it's more of a training tool, but I think if someone wanted to tear it apart, they could probably re-engineer it to where the computer could then be used to activate external effects, since it is affecting an external effect of an image on a screen. So it's called Shape Changer. It's not very big because it was made back whenever I think Windows 3.1 was basically just going out. So you need an older operating system from what I saw, though. I tried everything in the world, and anything past from Windows 7 on, I wasn't able to basically get it to work. So it requires something like Windows 2000 or
What was it? How about XP?
That's what I'm saying. I think XP and 2000 are the end of the limit of what you can get that program to run properly on. So, but I've used it successfully with other people and had fantastic results testing our abilities and seeing what the difference is between those who basically have been using it for a while versus those who come in fresh trying to use it. So
I think
quite
you
a few
can
people
use.
mad.
I think you can use those operating systems in virtual environments. There was a place, or at least I thought there was a place you could go and work in a virtual 3.1 or
Yeah, you should be able to run
virtual
them in like a
XP.
sandbox. So I'll have to look into that. So anyway, like I said, though, since it's abandonware, if anybody wants a copy of it so they can toy around with it, just let me know. It can be sent through email with no problem. So
Cool. Yeah, I'm working on a few ideas with my rotating liquid stuff. But since I'm so busy now moving from Roswell back to Albuquerque, I won't be able to have anything to show anybody for a little while. I'm trying to get an idea virtually or a mind experiment on how this thing would work. You know, I've done a lot of fails because I haven't had physics training. So I was pushing magnets around with electromagnets and, you know, sending them through glass tubes in a rotating disc. And I thought, yeah, I can change the weight of this disc from one side to the other on every half cycle. And then I thought, yeah, that works. And then I started looking at it and I think, well, for every action, there's an equal and opposite reaction. So every time I turn this electromagnet on to send the neodymium magnet, you know, to the up towards the middle of the disc, I realized, yeah, I was changing the center of mass on that disc, but the thing would change to make it wobble just like it was a static unbalance. I couldn't, you couldn't make it rotate every half cycle without it wobbling. And then, you know, Ron was telling me, well, and if you put this, you put a component in the liquid spinning, it self-balances. There's just thousands of little tests that I need to do to convince myself. I'm not theoretical enough to say, oh yeah, well, I should have known that when I move that magnet around with an electromagnet, it's going to move the center of mass to compensate for the change in center geometry, and it'll just go, it'll just wobble again like a static unbalance. So I just wanted to, what I call a dynamic unbalance. So I thought if you could get a dynamic unbalance where it's just unbalanced, you know, I don't know how you're going to do that without getting, you know, by getting around Newton's third law. That's the whole thing about acceleration with me, because when it's going around in a circle, it's in constant acceleration. And I'm still trying to put those ideas together with equivalence principle, because, you know, Newton in a linear elevator in space, you accelerate that elevator, it's an acceleration. It's not, it's a result of what gravity is. He says it's curved time space. Well, okay, so you're in that elevator accelerating linearly, and it feels like you're standing on the Earth at 9.8 meters per second squared. Well, if you're going around in a circle, you're also being accelerated in an angular system, and you're in constant acceleration. It's centrifugal.
I can hopefully answer something about that if you'd like.
Yes, I would love to hear it, because it'll save me a lot of time.
Okay. So dealing with the gravitational part, the mass attraction to another mass, if you have one mass and it's sitting in free space, and you have another mass that's also sitting in free space at some distance away, and you accelerate mass A towards mass B, as in you apply a force only to mass A, mass B does not have a force applied to it, and this only works in a universe that also has lots of other masses in it that are points of reference that can create their own fields and consequently sort of balance out the gradient, so it's fairly, you know, even all around us, like, you know, the universe that we have now. So this doesn't work in a universe where only those two masses exist, because they create an entire gravitational field gradient wherein they are all of the space because they're the only things that exist. So anyways, in this case, we accelerate mass A towards mass B, and we accelerate mass A in a straight line. So from mass B's perspective, mass A was sitting in one spot, and is sitting there constantly, so that the amount of gravitational force attraction it has is the amount of gravitational force of the mass that mass A has at the distance that mass A is located to mass B. However, when now let's say we have mass B moving at a constant velocity towards mass A. Let's forget the acceleration for now. It's just moving at a constant velocity. Mass B's field, because it propagates out at the speed of light, is effectively building up in front of mass B, and mass B's field is effectively being stretched out behind mass B. So if we accelerate mass A, sorry. Mass A's field is being compressed in front of mass A and being stretched behind mass A. So mass A's field, if we suddenly stop it here, the field of mass A moving along at the velocity of light in the direction of mass B is going to keep on moving out of the place where mass A stopped towards mass B. And when it hits it, mass B will experience all of the gravitational attraction of a mass that had the field of a mass that was existing in that amount of space for that amount of time, which will be much greater than that mass if it was static. See, that's an interesting phenomena, that you can actually make a mass appear to be much, much heavier along a certain axis, but only along that axis, only in that direction of travel. Now, onto your question of angular acceleration.
So go ahead.
Circle, it doesn't do the same thing, because the path of the force of the angular acceleration is constantly changing. So it doesn't build up in a line, and consequently you can't react against it in the same way. It's not such an unbalanced force. But there are ways to use it, because velocity takes part in all of this.
Interesting. Now, to get back on your first thing, mass A and mass B, mutual mass acceleration. When you're saying this gravity field, that it's pushing in front of mass 1 that's headed towards mass 2, for instance, you're saying that this gravity field is ahead of mass 1?
I'm saying that the gravity field is going to be wherever the mass is, and it's going to leave it at the speed of light. So if you were to move the mass at the speed of light for 1 second, then it would have all the mass of that entire thing that, let's see, how would you calculate that out? I'm sure there's some calculations for this to figure out what the actual mass energy would be if you moved it at some velocity c for X amount of time in a given direction. I know there's equations for this. I'm not going to try to do them in my head right now.
That's okay. Yeah. So, but what I'm kind of getting at, I guess, from what I understand, and it might be a relative thing. It's like if you're in the frame reference of mass 1, and you see you're sitting still, and it looks like mass 2 is coming towards you. Or if you're on mass 2, you're sitting still, and it looks like mass 1 is moving towards you. That's relativity, isn't it?
Yeah, but there is a difference. A lot of people wonder about the twin paradox and this idea of who accelerated, and it's confusing, because you're like, well, if it appears the same from both persons' perspective, how does one tell who moved? Okay, let's say that you.
Mm-hmm.
Sorry, give me just a second.
Sure.
Sorry. Okay, so let's say that you're sitting inside of a cylinder with a floor and walls and a ceiling, and you can't see outside. So in case 1, you are going to be rotated. You're not rotating yet, but you're going to be rotated. In case 2, the universe around you is going to be rotated, and you are going to remain still. Can you tell the difference between the two cases?
I don't see how, but if you got an answer for that.
In case 2, you are sitting still. You're sitting you're standing on the floor in the cylinder that's closed, and the universe rotates around you, you will stay exactly where you're standing and not feel any force. However, if we rotate you and not the universe, you'll be flung towards the wall. There is a way to tell, because there's an absolute frame of reference based on which has more energy and how long it's existed. And
Yeah, it took a lot of energy to rotate the universe. Yeah.
right. So the thing is, it's causality, because the most recent event, the most recent radiation of energy, as in a change in the physical location of all charged particles, was your event where we rotated you. And because it was the most recent thing, you experienced the difference in the change because it happened at your event. And now it has to propagate out at the speed of light for the rest of the universe to realize that you rotated. But the rest of the universe has already been sitting there. It's already been existing. So, you know, it's not gonna have the same effect if you don't move.
So like I'm moving right now here, and I'm sending out a wave. It's affecting everybody in the universe at the speed of light when it reaches them. But
Yeah,
it's inverse square, so it's going to be a real small force.
Every piece of mass that moves creates a little wave that travels out at the speed of light, which is also a variable based on the refractive index of space, into the ends of the universe forever. And that effectively creates the space between objects. That's where you're getting your physical space from. That's why there's so much more energy in space than there is in matter, and why space is so much larger, as in there's more space than there is matter. Matter takes up a tiny, tiny, tiny little amount of the actual physical volume of what we call the known universe. And the reason for that is because the longer electric energy, magnetic fields, the longer these things are radiated out, the greater the space becomes between them, because these fields never die off. They just permanently keep on traveling. And because they continue to persist, but the particles that produce them never die off, the ratio between how much physical energy the two contain continues to get larger and larger and larger.
So out there on the fringes of physics, the last speaker we had, I watched him. I wasn't able to be on the whole thing, but I watched the recordings talking about trying to find dark matter, trying to find evidence of it in those drums of liquid underneath the earth, you know. So we don't know what the dark matter is,
Or if it exists.
or if it exists, right? I mean, it's all a mathematical thing to make the balance of the equations, right? And the dark energy too. I assume dark energy is not connected to dark matter. Those two things.
Well, they're both dark.
You can't see them, but there's a lot of energy in that dark energy. Oh,
So,
well, like
Jeremiah, I had one question about your description of one mass going towards the other, and how that you're basically saying so basically space-time in between the two masses, they approach each other, is denser. And
Well,
and thinking about it at the subatomic scale or the atomic scale, what happens to the protons and electrons? Isn't it like become egg-shaped, where the pointy part of the egg is where the proton is in the field, and then the electron comes out in like a parabolic kind of orbit?
The answer to that question is it entirely depends how you accelerate your mass.
Okay. So
if you push
it's
it
constant acceleration.
Pull it from the front, you're going to refract it. If you accelerate it uniformly from the sides, you're going to have a drag in the center mass. If you somehow can grab onto all of the mass simultaneously, magically, with your device that can couple to every piece of mass all at once, then, well, you'll have a perfect acceleration field. But in either case, what you're going to end up with is, based on its velocity compared to the speed of light, you're going to get that compression for however long it was spending going at that speed. And that's a field effectively that once it builds up, you're in your own field, but if you suddenly stop and you leave your own field, as in, you're no longer moving that velocity, you suddenly decelerate down, that field doesn't just go away, it continues to move. So if someone came out of warp drive and they stopped very, very close to a planet, the gravitational wave produced by their sudden stopping, that momentum from the mass that they had built up traveling that velocity at the speed of light, say, for example, or faster, is going to suddenly come rippling back out, and it's going to slam into whatever's in front of it in almost a beam-like configuration. And so if they had
X-ray.
if they exceeded the speed of light, there would actually be a gravity suction beam that would pull on anything that was in front of it. And if they had just gone at exactly the speed of light, all of that mass energy would effectively just be a huge force beam that would slam into whatever it hit, sort of like Pakhanov's force beam.
But that
Which
would
I believe-
assume, wouldn't that assume that gravitation and electromagnetism are connected somehow?
Well, they're connected in many ways by means of the fact that they both have to propagate through the vacuum. And in doing so, they both have to follow a couple of rules, meaning that they propagate without a variable refractive index that's different, or for any other reason, through the pure vacuum with nothing in it. They both propagate at velocity c, right? They both die off by divergence by the inverse square of their distance. They both follow effectively a lot of the same rules. So you can use the same types of understanding to map both systems. And yes, they do produce the same types of unbalanced phenomena. If you move an electric charge, for example, along a straight path, the same exact thing happens to the electric field of the electric charge as happens to the mass field of the mass. You get a buildup of the electric field, and it appears as if you have a very, very large amount of charge, which is why we measure fast-moving charges not in velocity, but in electron volts, meaning that this one electron, which normally has 1 electron volt of charge, now, because of its velocity, has the same amount of energy as 100 electrons, 100,000 electrons, 10 million electrons, because it's moving really fast. So the actual electric charge field that it has is as strong as 10 million electrons in that same point. That's effectively what that electron volt number means when we talk about particle accelerators, is that electron has gained relativistic mass and a consequent relativistic electric field, which now makes it weigh more and makes it have a much greater charge. So all that needs to be considered.
But the example of tunneling shows that you can actually go superluminal. It's not really going superluminal, but isn't the vacuum or empty space just another type of barrier, like in a tunneling?
Well, yeah, then there's the theoretical idea that the charges themselves may somehow be in a geometry that can modify the refractive index because of the gradient that's produced by their motion. So say they may be in some kind of strange phase or strange state where they actually can go superluminal without technically themselves moving superluminal.
Right.
So
So
they
an
create-
example I was thinking of is I heard about this observation where they had a star that was falling into a black hole, and it popped out the other side.
What?
Yeah,
What?
it popped
What?
out the other side. It didn't get absorbed. It just
It's
tunneled
right
right
next
through.
Oh, right. So what happened to it? It didn't like fling it away, did it?
No, it just popped out the other side of the event horizon. It's like a jet and a black hole. When the jet's coming out on this side, the other side, there's a jet coming out at the opposite spin, just like an electron at orbit around a proton. That's what happens in protons. The electrons tunnel through the proton. It happens all the time.
So you're saying that in this case, instead of this object sort of disappearing into the event horizon, taking some long period of time and then popping back out, it was pretty much in one side, out the other instantly.
Yep. They observed it. Well, they can't say instant, but yeah, that's what it looked like.
But at the resolution limitations of whatever astrophysicists have right now, we observe what we believe to be this thing that you're describing to me. So
Right.
very interesting. Very interesting.
Yeah, I thought
indeed.
it was pretty cool too to see a tunneling example at the cosmic scale. See,
Hey, Michael, can you hear me? There was a group observation of the Sagittarius A black hole, which is the
There you go.
supposed black hole in the center of the galaxy. And there's this G2 object. And it was a group. It proves that there's no black hole in the center of our galaxy, because it just goes, it swings through. I was just
Or
talking.
where it's an event horizon, you just can't see it.
No,
No,
this
there was a distortion though, so there's like a heavy gravitational field. That's what really confused them, is that it didn't just wander through like empty space, but it didn't get sucked up like a black hole either.
okay.
Now
So
they're supposing that might be dark matter that's creating the gravitational pull at the core.
no, it's the plasma toroid jet model. So like, let's go back to Robert Forward's paper, and like you have a bunch of charges moving around. He has like a poloidal as well as a toroidal, but just apply that to the stars in the galaxy, right? They all have an electromagnetic moment, and they're all whizzing around the center of the galaxy, the barycenters. So they generate a fake gravitational moment, or a virtual black hole, and then it's, the laws of electromagnetism are applicable at the galactic scale. We're just not doing it. That's like the whole where detection of a drag force in G2's orbit, measuring the accretion flow, something. Here, let me get the full archive. Measuring the density of the accretion flow onto Sagittarius A at 1,000 Schwarzschild radii. And it's this huge group paper. It was published on December 4th, 2018. Tuesday. Yeah. So that paper, that is like empirical evidence that there really isn't a black hole at Sagittarius A. It's more of the dynamic, the addition of all of the stars' moments circling around the galaxy create this thing
So it'd be like basically taking the planet, separating it apart evenly, but it's still equally like distant. All the particles are, so you end up with a lot of black volume in between. Still has the same gravitational field at the very core of where that planet was.
No, it's the stars itself, like Sol. Like our sun is a nuclear fusion reactor with its huge electromagnetic field, right? You can see it in Jupiter as well. But they're all of the stars whirling around. It's like dust. I don't know if you've ever played with an XY table on a router, and you have a vacuum tube on it and it's cutting out wood. You have to run ground through it because all the particles zipping through the tube in a vacuum creates static on the outside of your dust collector system. So there is dust. There's this, the stellar water that gets blown out of stars. So there's, it's that Sam guy a couple of weeks ago was having at that the dark matter physicist from New York, the plasma toroid jet model, or plasma cosmology, and Anthony Perret. He worked up at Los Alamos, and his physics on plasma cosmology were declassified a couple of years ago. So it's there may be black holes, but I mean, I've studied through the mathematics, and it's, Schwarzschild came up with the solution, a field equation, and it had a 1 over infinity. So like infinite smallness, and they just called it a singularity, and we've been stuck with it ever since. So there may be black holes, but there's plasma cosmology, there's, it's the electromagnetic moment of stars. I mean, one of the things that clicked after seeing optical cloaking, neutron degeneracy, right? Like the neutron stars, there's no more external magnetic field on a neutron star. So light can't interact with it. Like it's, I guess, getting absorbed or whatnot. And so some of these characteristics of black holes are ascribed to degenerate matter, and we're still in this mess, academic mess of like, ooh, a singularity, and it's synonymous with death. and it's, oh, I'm going to die one day, so the mind clicks onto it, or the average person's mind thinks it's terribly fascinating, but it's a mathematical concept. The crowd has been running wild with it since World War I, and we're slowly finding out that there's better, you start applying electromechanical dynamics, this plasma cosmology.
Well, when I first heard about black holes, I figured it was proof the whole universe sucks.
We got to remember black holes have no hair. So anyway, it's a dirty joke from like the 60s.
You have to understand that the universe both sucks and blows simultaneously at
That's
the same
right.
time, though.
Yeah, I called it.
Sucking and blowing.
I called it the frat boy theory.
Continual expansion.
So yeah, it's really kind of cool that all this stuff. It's all the walls are getting torn down is what's going on. As more and more information comes out, it's like at one point did they say that all physics had been discovered?
Oh yeah, that guy.
Remember? So and it's like now it's like we don't know nothing.
At least the consensus is becoming the wise consensus of we don't know nothing, instead of it just being the isolated few free thinkers that seem to be on the fringes of physics. I do like what's happening.
Well, even the military seems to be admitting we don't know nothing either.
I'm glad to know that we've had our part in helping that along at APEC and making this event happen. So
yeah, I'm with you.
This is a lot of fun.
Yeah. Now, what I'm hoping is that and that's kind of the reason why I keep bringing up these like seem kind of esoteric, like non-violence and intergenerational trauma and stuff. Is because those are the folks that I think are dealing with a lot of. I mean, it's not just the stigma that they have to overcome, but just think of all this internalized trauma that they've had to do because of the job they have, just where they're at. And so why would anyone want to stick their neck out and say anything where they're going to get criticized when they've probably been dealing with it? They've been internalizing it for so long. And that's why I think we got to open it up, making it so people feel comfortable talking about it.
That's why I like to hide behind my, I'm an artist, not a scientist. Because if I try to be like academia, then, they all jump on you. The first mistake you make, like I said the other day that light was traveling at 300,000 meters per second. I said to this lady on one of these APEC conferences, nobody said anything. Well, I was off by like 3 zeros. It's just 300,000 kilometers.
Close enough.
And then I told her that the Voyager was going 1/3 the speed of light, because I googled it real quick and it said an ion engine could make it travel at 90,000 meters per second or something like that. So anyway, I just thought I'd clear that up. And, nobody trolled me on it or anything. I only got one troll on my website. And he said, no intelligence found here on this troll comment. No intelligence found on gravityalchemist.com.
Well, criticism is an expression of an unmet need. That's all. Don't hear criticism. It's people say stuff to you that, especially people you're close with, that they'll get angry or something. They'll say something totally the opposite of what they meant. It's not. Somebody's trying to express something. They have a feeling. It's about feelings and needs, and people don't know how to express their feelings in our culture.
Mm-hmm. Oh, and like the academia, you got to be careful, because as soon as they catch you on a mistake, they're gonna do like Eric Lathwaite and say, he didn't know what he was talking about. The guy that invented all of the. I love Eric Lathwaite. I love the spirit. I was like a kid listening to him, and I guess the Royal Academy or whoever it is over there in England, after he started doing those things about gyroscopes, they were all getting shaky and kind of took him off the air.
Shadow ban.
Yeah. Yeah, he got banned. He got somehow, you get the really smart ones, either they're jealous or they just catch you on something and then get you out of there because you're either, you could have, he could have went on and really done something fantastic, which he had already done with magnetism and the maglev. It was incredible.
I wonder if this is like a remnant of like the attempt to stifle scientific investigation and research by everyday people that's been going on for quite a while. Basically, like they pulled the golden age of chemistry experiments or something like that, or a little golden book of chemistry experiments, because it was too dangerous. And this guy that died in like 2016 because basically when he was a teenager he built a nuclear reactor in his garage, so which he was being pushed at the time by to get a radioactive badge, because back then they were still pushing to improve like the knowledge and whatnot, and the construction methods and whatnot to get nuclear on U.S. soil as an energy source and whatnot. So they were even pushing the youth to basically get involved in it. And now since then they've been just like been pulling the rug out from underneath everything. Everything keeps getting more and more nerfed until eventually the only thing you have in science labs now are books. There are no
Well,
tests.
it's kind of like what the Woz was talking about. We used to, it just seems like when I was younger, everything was open source. If something didn't work or broke on my oscilloscope, I'd go look at the manual. I mean, in some ways it's better today, because if something breaks, I can go on YouTube and say, how do I change the klystron in my microwave? And there'll be a video there to show me how to do it. Okay.
That only applies though to areas where the company that made the part isn't putting a chokehold on the company that makes the individual components for it, so they can't sell you that part too, which is what the right to repair movement he was talking about was all about.
Right. So like I have a wall furnace, for example, and I can't buy the thermocouple. I have to buy a whole new wall furnace because you can't go buy the thermocouple at Home Depot, right?
Right. And part of their excuse is, oh, well, we want to be safe. We want to keep you safe. What's your plan if they make a mistake? It's like, it's not my plan to solve anyone's problems. They have to make their own choices. I'm not taking their rights and their choice away from them. That's the whole point. You don't need a plan,
Well, I mean, computers, I would get it. My son, for example, he's like 30 now, but I remember when he was like 10, he built or 12, he built his first computer, and he bought all the stuff online, and then he watched some videos online, and so he knows how to build computers. Now, I learned how to build computers back when there were like 286s. Right? So it's like, but because I did that and I knew how to do it, there wasn't a barrier to him learning how to do it himself. But if you eliminate that, ability to fix it yourself, you're basically stopping innovation.
Right. Yeah, that's what they're pushing. The people that are opposed to right to repair, like Apple and whatnot, they're saying, oh, well, if you let somebody else repair your phone that, is not Apple certified, they might leak your data, or they might install TikTok, or they might do this, they might do that. And it's like, well, then what about the guy that worked for Apple that released that woman's nudes on a phone that he didn't even know who she was? He just was supposed to repair her phone. Then he grabbed her data and just spread it all over the internet. You're not any safer with Apple than you would be in fact, you're safer, I think, with a third party, because they can't afford the millions of dollars worth of lawsuit that Apple can. Right. You know what I mean?
Yeah.
Well, there's another there's another side to this that I thought was really interesting, the Moore's law concept, Moore's law, and I hear Michio Kaku talk about this a lot, that things are getting less and less they cost less and less. That pretty soon the paint on your wall will be like computer chips. Everything will be, they make them out of dirt, and it'll get to the point where they don't cost anything, and you have all this technology and all this binary information, all the powerful computer, and it could be in the paint on the wall.
Well, I'd rather leave it off the paint on the wall, William. I think enough. We have enough monitoring going on. I think we need to have days where we just leave our electronic devices alone, because I think we become too dependent on them.
Well, yeah, that's good. At some point, yeah, when you go to bed, you should make sure all the little red lights are off in the bedroom. Everything's off. It's dark. You let your mind relax. The
red light's less damaging than if you had blue LEDs or something in there too, though. So
exactly, no lights at all. No lights at all. Well, I guess there's a whole science of that too.
I actually can't sleep without sound because I'll roll around and grind my teeth and whatnot, and that actually like a white noise gets me to basically focus on that, I guess, while I'm asleep, so that I hardly move at all. I don't grind my teeth or anything.
So you said in the chat, Thomas, that your power went out?
Yeah, my lights just all clicked off. The only thing I have hooked up to battery backup right now is the computer and the monitors. So, which I'm on a headset, so
So you have a
thunderstorm.
Oh wow! So that
Yeah.
knocked out your grid, huh?
Yeah, well, it caused it to glitch. Everything had to it was basically just breakers or something. It wasn't like transformers exploding or something.
Oh, but you have
I've seen that
battery
before.
backup.
Yeah, just a UPS. I've got a UPS on this, and then in the other room there's a UPS hooked up to the router and gateway and whatnot. So it didn't affect all of the lines either for our DSL either. So
Huh, that's interesting.
just the
But
AC
just
power.
the power lines.
Yeah, just the AC as always. The thing that keeps your food from going bad.
Yeah, well, I have battery backup too, so
We need to get on that energy source so that we can basically have independent power sources in every place.
yeah. Well, I have solar, and I just installed new batteries, and then I had these old batteries, and then I bought this thing here. Let's see.
Is that an inverter?
It's a 12 volt, 8 amp, 24 volt, 4 amp pulse repair battery charger. And what it does is
so you can keep using your batteries by desulfonating them.
it desulfonates them, and what it does is it makes it rejuvenates the leads, and it makes it form into these little domains. So by using a pulse. And
Right. You know why they're using a pulse to do that, though, right? As opposed to just constantly hitting it with a high voltage.
Oh, we probably break it down if you did that.
Heat. It's the heat.
Yeah, it's a heat thing.
It allows the heat to dissipate before you hit it with the next pulse. Because they do this, they do exactly what you're talking about to make the batteries in big vats, but they're not enclosed in a container that the heat can't escape. And they just constantly hit that lead with that material in order to activate it, to turn it into the material that you can then stuff into your batteries.
Well, it restored them.
Charge.
So it's the point, and they're like 250 amp hour batteries, 12 volt. They're huge.
They're lead acid though, like glass.
They're all lead acid. So now instead of when I install those back in, instead of 4.8 kV battery backup, I'm going to have a 9.6 kV.
Oh, nice.
4.8 kV gives me a day and a half of power. So I'll have 3 days of power.
Right.
I live in Pacific Gas and Electric territory where they'll black me out if the wind blows too hard or if it gets too hot or if there's a
Yeah.
fire over the mountain or I mean at the drop of the hat.
It's all down to whether they've updated or not since basically initial install and how much wear and tear it's taken. And they tend to let that stuff run way past its lifespan.
Oh,
Or
I
it should
know.
be,
Well,
you know,
the
reopened.
problem with PG&E is they're not maintaining the lines, and so what happens is they get arc flash to the trees and stuff, and that starts a fire. It's like PG&E's been sued so many times that they had to go bankrupt like 3 times now. And then they stick all the ratepayers with the bill.
And like they restructured not and to
Yeah,
avoid
they
having to pay
restructure
out.
and then they take on a huge debt load to pay back all the insurance companies
Right.
and the lawyers. So, and now my big pet peeve is they have this thing where if I go ahead, I could go flip the switch now and just like disconnect from the utility altogether. Well, it turns out they're going to charge me a fee, a departing load fee, they call it.
That box, that's about 1,400 watts worth of just the solar cells. So I'm not working on something to use at the house. I'm working on something to take on the road. Like it's going to be packed up in
Oh,
the
cool.
pickup and pull it out on site and whatnot. I even I don't know if anybody needs anything like this, but like if you need a permanent canvas like structure, an awning on a like say a skyscraper or something like that,
No.
just look up the companies that make awnings for for your local buildings, because they throw the old ones away and they still have years and years of life left in them. Just have to clean them up and whatnot. I picked up one. It's probably it's close to like a kind of circular shape, like a lily pad. That's about 35 to 40 feet, depending on which direction you're measuring it. And the thing weighs about 150 pounds, just for the tarp.
So my solar panels, I got them in 2002. And they're still working fine. So, but I gotta check out, folks. My better half just came and indicated my time's up. But I had fun.
Well, Michael, thank you for
And
joining
thanks.
us.
Sorry if I pushed the boundaries a little bit there.
Oh, it's okay. Yeah, a couple of people were like, "This doesn't fit." I'm like, I understand where he's coming from.
No, I understand too. I just,
yeah,
I'm just being me.
no, I get it. I think we're doing good. So our next one, I think, is going to be July 31st. I have to skip to 3 weeks because I have to go out of town for my wife's thing. So July 31st. And then after that, we're probably going to do live from Tesla Tech, which should be totally off topic, but probably a lot of fun. So.
Oh yeah, that's going to be epic. Live stream from Tesla Tech. By the way, the 31st, I wanted to do a special APEC focus kind of conference on theories of everything for the 31st. So I wanted to invite David Chester back. And I've also I'm hoping to get Ken Griggs of the Phoenix theory to come on and give a presentation and also have a discussion between him and David Chester on deep physics. So that should be super interesting. I'm also trying to reach out. I've been kind of in loose communication with Eric Weinstein, and I'm trying to get him to come on to talk about geometric unity, but I don't know how likely that is to happen unless I can get him super interested. But yeah, that's what I'm trying to do, is to do a focus APEC on theories of everything and deeper, physics kind of stuff.
I'm going to make notes on that right now. Theories of everything. And do you want to reach out to them, Jeremy?
Yeah, I just sent David an email. I've already got Ken, I think, confirmed. So I've also reached out to Eric, and I'm going to try to reach out to a couple other people.
Okay. Yeah, and then Remi had another fellow, Daniel Sheehan. Different. I think this is different than the Michael's guy that he was reading earlier. Same name. Daniel Sheehan, University of San Diego, or san diego.edu on
Is that
second
the
law
lawyer guy
research.
from Disclosure Project?
I don't think so. I think it's the same name, but a different person. This one is going to talk about second law research and retrocausality. So he was going to talk about basically things that violate the second law of thermodynamics. I think he's on August 14th, I believe. That's where. And then Stephen Lutz, we were hoping to have him for countering inertial effects with type 2 superconductive flux pinning. And he might be on the 31st. And Remi recommended both of those gentlemen. So. Oh, and then Jason Sakaris, also from last session. And he is tentative. I don't know what date yet. So. But yeah, here, I'll share I'll put this in the chat. That's our schedule. Yeah, so anybody with that link, you guys can view that spreadsheet. That's kind of what I've been working on lately. So we have a bunch of tentatives. I mean, we have tons of tentatives. We'll see where things go. But yeah, if Ken and David Chester want to come on, that's awesome. And then Jeremy, have you thought about doing something more on UAPs? I mean, you did one heck of an overview a couple weeks ago.
Yeah, well, I think all these topics are loosely related, and you know, we should be a recurring theme for discussion at these conferences, because well, we have engineers and physicists together to talk on a scientific level about these things. I think we should do another. And that would be great if we can get Eric Weinstein to join us for a discussion on that, because he's posting all over Twitter saying that he's looking for scientific groups to discuss this topic with, or that are diving into this. And I'm like, well, we got the group, man. Like,
I'll put him down too. Eric, do you think you could reach out to him and see, maybe he'll show up?
I'm trying, you know, I've been in touch with his brother Brett, but I'm trying to reach out, because he'd be a great asset in this. And with the stuff that he's been posting on Twitter, it's great. So
yeah, good deal, man. Good deal. Well, good conference session. I think it was exciting. You know, we had some different
yeah,
guests.
I'm gonna go ahead and end the live stream here on YouTube. Thank you everyone who is watching this live, and for everyone that tuned in.
Deal. Thanks again, guys. I'm going to shut things down too.